Hello, welcome everyone. I would like to present our next speaker. It's André Suri from ISC, who will be talking about bind9 code quality. I don't think this is actually a DNS talk, is it?
No.
Right, good luck.
A little bit. So, just to get a feeling of the room, who knows bind? Who uses bind? Okay, who is a developer here? Oh, so many. No. I would know something about it. And who ever programmed something about DNS, like DNS developers? Okay. So this talk is more about like what we are doing to bind at the moment. So it's not strictly about the DNS. It's more about the bind, and about the concurrent programming. So my question would be, who does threaded programming? Okay, quite a lot of hands. There's a couple of prerequisites for us in bind, and that's continuous integration, because if you don't use the tools I'm going to show you on a regular basis, it doesn't make sense at all. So if you ever use the tools, just integrate them into your continuous integration, and then you have to have the time to fix all the bugs. So about bind, it's a 20 years plus old code base. So you can imagine it's pre-C99 code sometimes, and it's getting better. It's multi-threaded. It uses locking. It has its own RW lock, which have some advantages, like it allows downgrade and upgrade. And since bind 9.14, which is current stable, we are right now just before the release in 9.16 stable version. It uses the STD atomics or the shims for in GCC or in Windows API. So I don't know if you can actually see that, but there are a couple tools that we can use or we are already using, and it's kind of built from Clang. I'm going to talk about a CPP check. There's also Clang Tidy, which does a different kind of checks. We are not using that yet. For the runtime analysis, there's a lot of sanitizers from GCC and LLVM, which are very good. And there are some commercial tools like the Coverty scan, which can be actually used for free for the open source projects. There's something called Sonar Cloud, I think, but that's like very chatty. It reports all kind of weird stuff that's not even like, it has a lot of false positives for us. And there's lookgoodtome.com, which also looks very good. And the last tool we use for bind is Cosinel. It's very good tool for refactoring large code bases. It's mainly being used for Linux kernel, but we are using that too. So what's the scan build? It's static code analyzer. It works by replacing the CC and CXX environment variable, and it comes from the LLVM and Clang suite. So the usage is quite simple. This is for the autoconf based projects. You need to use it for configure, and then when you are running make, you keep the CC variable set from the configure step, and the output is this is just one of the commits, because we try to be more verbose than just fixed bug in the commit messages. So this includes the real reports from the scan build, and it finds that like little stuff. The bind code base is quite good in regarding the scan build. So it found like small stuff, like the result is never used, and so we fixed that, obviously. Then the CPP check, that's a different tool. It's an independent project, also static code analyzer. It's more difficult to use if you use autoconf, because it requires compilation database, which is a JSON file with which includes all the configuration options and C flags and LD flags and the path to files, and and you need to build a compilation database. So there are some tools that can build that automatically, like I think CMake and others. For automake, it's more complicated, and it has a different level of strictness. The most strict level is crazy at the moment for bind. I'm not saying it returns false positive. It returns good stuff, but we are not there yet. So this is the usage. So you run configure, then you for automake use tool called bear, which is I think like shortcut for build ear. So it listens what goes on, and then you run CPP check on the compile commands JSON, that's the compilation database, and it runs the scan on all your source files. So it's important to run your project in like a debug mode or enable everything in the configure so it gets analyzed. And the output looks like this. So it's this is output from the tool called CPP check -HTML report. And you are lucky because the CPP check 1.90 just came out and it found a new errors because we were CPP check clean before. So this is from the CPP check 9.90. So it found a new errors. And then if you click the individual error, it looks like this. So it's annotated your source code. And it shows the path through the file, and it's very good. So if you are developers and not using the CPP check, I invite you to do so because we like it quite a lot. The next tool, the Cosinel, it's a program matching and transformation engine, and it has something like called semantic patches. The usage is that you call the command spatch, then you pass it a patch, the semantic patch. It can work on Git repositories, and there are some other small options. So and it outputs the number of files it matches according to the rules. And then if there's anything that needs to be patched, then it either outputs the patch to the standard output, or you can like patch the files in place. There's an option for that too. This is a very simple semantic patch. So what this semantic patch does, that if it finds an assertion, for example, if you have a switch command and there's a default which always asserts, like this is like custom bind assert, it insists 0. So if the code reaches the point, it crashes with assertion. So it adds ISC unreachable, which is actually just macro to attribute that the end couldn't be reached. So it adds the ISC unreachable to all occurrences of the insist where it's not already there. So that's the condition behind. I'm sorry for the Unicode character. It's actually the normal asterisk dash, but the font kept like changing that. And this is a more complicated example. Recently we made a change to the bind allocator. So ISC memget cannot return null. If the allocation fails, the bind will crash, because if you don't have enough memory, then you have different kind of problems anyway with the current allocators in modern operating systems. So this tries to catch all the occurrences where there's a statement which is you declare a statement S and then expression V. So if V, like a variable, is a null and then follows the statement, it just deletes the whole block of the with the variable. And there are some. It's quite smart. It even can understand. So if V is not null and there's a block and there's an else statement, you can just keep the other block, which is the condition on the first block on the right with the S1, S2. So it can do all kinds of transformations. So it understands the C code and it transforms the code properly. So it's not like a like find and replace. It understands the C code and can delete the whole statements or transform them into something else. Again, if you are working with an old code base like Bind is, and you need to do extensive refactoring, this is very cool tool, and you should try it. So there are some more examples how to do stuff with Coccinelle. There's a web page. We have a directory with all the semantic patches we used in Bind, but they are very Bind specific. And there's coccinellary.org, which has even more examples in a Git repository. So why? And here comes the fun part. It's not so funny if you have to fix all the bugs. So who understands the memory ordering? Oh, I'm lucky. I can tell you whatever I want. On a platform with weak memory consistency. Okay. Me neither. Well, I'm trying. So, and what about memory barriers? Like, do you know what's that? Okay, 1, 2. So, and bonus question, what's lock elision? Would anybody know? Okay, I'm not going to talk about lock elision, but it's a feature on Intel processors, maybe on AMD too, where you can like not lock things, but when they collide, you roll back the whole transactions on a CPU and memory, and you actually do the locking, so you can avoid some locking on the hardware. Very cool, but I'm sure there are some bugs hidden in there, especially with Intel. So thread sanitizer. This is runtime analyzer, so it doesn't analyze the static code, but it analyzes the like running code. It requires a good test suite to run, or you can like run it on your production if you are brave enough. And it checks for data races. Like if multiple threads access the same memory location, mutex ordering, so if you have like multiple locks in place and they are locked in different order from different threads, so there's a possibility of deadlock, and other subtle errors in the thread programming. The usage is again quite simple. You just add a flag to C flags or LE flags. Well, you need both. And for Bind, we need to, I told you we are using our own implementation of RW lock. So thread sanitizer doesn't understand that, so we need to use the standard pthread RW lock here. Then you build the program, then you export some extra options. Because Bind is quite complex, we need to increase the history size. It's like the amount of memory the thread sanitizer used to keep track of the memory locations, and some other options which make it more cleaner, because, for example, the log path tsn basically means that the output is logged in the separate file and it's not mixed in the standard output. Exit code again means like, usually it exists with exit code 66, but if you are running a test suite, you usually don't want to stop the test suite because it failed. So there are some like options like this. Then you run a test suite. Bind has both unit tests and system tests, and then there's an output like this. So as you can see, there are data race between the two threads, and they are similar location, like ISC, NM handle, unref, but there's a data race, and it's quite interesting data race because this is the unref function. It uses reference counting, and if the reference goes to 0, which is the function ISC ref count decrement. So if it's not 0 yet, then it returns. But if it's 0, then it deallocates resources. That should be correct, right? So why is there a data race, especially in this function? So it properly uses the reference counting. And then the free function, which is called here, it just allocates the resource and that's it. It clears the resource and then the memput is basically the ISC version of free. And still there's a data race. It looks like innocent in a course, right? So the fix is to add a destroy to the reference handle. Why? Because the refcount API uses the standard atomics, and the decrement function uses the memory ordering release, and the destroy function uses the order acquire. And to actually understand this is from the documentation. So if you don't use that, there's no synchronization between the threads. So the destroy function, the missing destroy function made one of the threads not to synchronize with the other during the decrement. And then there was a data race because of the missing release load. And okay, so who now thinks understands memory ordering? I understand memory ordering and the atomics more than I understood them a year ago, but I'm still like, another example. There's a data race on the PowerPC 64 reported by Red Hat because they do have some interesting hardware. And it's caused by our own RW lock. And the proposed patch, again, changes the memory ordering from relaxed, which doesn't cause any synchronization, to acquire, and the compare exchange operation, again, to acquire. On a synthetic benchmark, it works. I just look at the function, and I think that basically there's an error in our RW implementation, but we haven't seen it because the usual hardware has a strong memory consistency, and it doesn't manifest. So it manifests only on the PowerPC 64 because it has a weak memory consistency. Again, like, so, but I think that there's a lesson to be learned here. So to my, I like the saying, don't do your own crypto. And I would add, don't do your own locking unless you absolutely know what you're doing. And the good news is that in a new version, by 9.16, we are actually running a benchmark now with the system library RW lock. And with some other tweaks, we are over 1 million requests per second. So just dropping our own RW implementation increases the performance because we changed the other parts of bind. So that's good news. We might be dropping the implementation at all. Another example. There's a comment. No one else has this socket, so we can free it, right? And the fix is actually to lock the socket structure because, again, there was a bug which no one else has the socket except when you are on FreeBSD in a VMware on a hardware with a lot of cores. It was very hard to reproduce, but it was reported by the FreeBSD maintainer. And thank you for all the work he does by reporting the bugs to us. But it was very weird bug. We tested with a lot of cores on Linux, but it only manifests on FreeBSD in VMware. if anybody can say me why, then I would be happy to listen. So another thing on FreeBSD. We added to our continuous integration, we added FreeBSD and Windows in September last year. We also added OpenBSD, because if you don't run it in the CI on every merge request, then it's like it's not happening, because the developers are going to ignore the reports that came asynchronously. And there was an intermittent failure in the FreeBSD system test job, and it was a crash in the libthread system library. And it was a OpenSSL exit concurrency, because OpenSSL 1.1 automatically destroys the resources. But if you have a multiple threads running and shutting down the resources, then one of the threads were destroying the mutexes held by the OpenSSL before the OpenSSL on-exit functions ran. So we had to request there's an internal task manager in bind. So in a fatal function, you have to request the exclusivity of a task manager, so it finishes all the other stuff before it crashes. Again, it was very weird, because we were looking why it's crashing in the system library. Here's the quote from the documentation. The other type of debugs is the log order inversion, and this is actually the cycle at the beginning is quite short. I have some 8 mutex long bugs in bind at the moment. They are not yet fixed, but it looks like mixing the mutexes in a different order from different threads. Just an example how it looks. The most simple thing you can do is to convert the locking to, because there's a lot of flags in structures, so we just converted this flag, removed to standard atomics, dropped the locking at all, and it's protected by the atomics. And now you have to get the memory ordering right. So are we there yet with the thread sanitizer? Not yet. So this is the current result on the bind master. There's 10 distinct warnings from the thread sanitizer, but there's something like more than 200 different paths to the warning. There's a lot of duplicates, like these 6 errors are probably the same one. And in the log ordering, there's probably also a lot of duplicates. So it's not that much bugs, but we are not there yet. It doesn't crash on a regular basis. It just sometimes something happens, and we don't know why. And getting this clean means that we can run the thread sanitizer in a strict mode. So if there's a new warning, it will stop the merge request from being merged. And but as I said, we are not there yet. So thank you for listening. And if
We have 7 minutes for questions.
you have any questions, not about memory ordering, please.
I have several.
Just a very quick one. Did you also enable more compiler warnings over time?
Yeah, we run with W all, W extra all the time. And we also have in the CI, we have multiple jobs. So we run with Clang, we run with GCC, and we run with different optimization options, because sometimes it also, if you run with -0, sometimes it reports stuff that's not real bug, but it I don't know, there was a code that's if there was a variable 0, it didn't run a loop. So on a higher level of optimization, that got optimized out, but on a lower level optimization, it printed a warning about something. So again, like trying different optimization options from -0 to -03 is also a good option in the CI, because the compilers do a different stuff. Also, running the thread sanitizer with Clang and GCC bears a different results. So that's also a thing you should do if you're running the sanitizers. Just do the different compilers, because they created a little bit different code.
I see a question. You just talk loud.
What was the tool for code coverage again? Concurrent?
I don't know what is our code coverage at the moment.
No. I mean the tool you talked about. I think it was the second one.
You go back like 30 slides.
Yeah, this one.
Questionnaire.
Okay.
Question here.
I would like to ask you about C++ check. You use this tool to try to find bugs or exceptions in your code. Is it possible to use it for checking coding style?
Well, bind is written in plain C, so but I don't know if the C++ check.
CPP check.
CPP check. Okay. Yeah. You mean this one?
I mean this one. Yes.
This
Is
one.
it possible to check just coding style?
Some, yes. On some strictness level, it also reports like variable scoping. So when you can reduce the scope of the variable, and some others, it's quite extensive list actually. So, but it would be moot to just show it here. But this is what we use. So this is from our CI, the line. So we are just using these. But I'm in the Emacs camp, so and I do my coding in Emacs. So I use flycheck to run CPP check and Clang on my code, so it automatically like highlights the issues. I'm probably sure that the stuff that the young people use, like all the IDE, so that it does this as well. But the Emacs, I like Emacs.
So what's bear make?
Bear make, it creates the compilation database from
Right.
it.
Okay. Any other questions? So are you finding that CI is very expensive or slows down your team? Because I found that those are the options.
So right now, we are using like hosted bare metal servers, and we have like 8 of them to run all the CI, but we have something like 56 jobs at the moment. So it's getting slower and slower as we add more and more tests. We also have a Windows in the CI, so it just consumed one of the machines, but the other machines are shared. So if you are OpenBSD is ran in the QEMU. FreeBSD had also consumed its own machine, and it uses jails. We wrote a plugin for GitLab CI to use jails in the GitLab CI. And also the OpenBSD, that's also our own plugin. For Linux, it uses the standard Docker, but for the other systems, we had to write custom executors for the GitLab CI. So define expensive. So if it catches a bug that would cause a CVE later, was that expensive?
No. But I found in some teams that it can scare people off. Like you say, we're going to spend $1,000 a month now on just testing the code all the time.
Yep.
They say, well, can't we do 100? And well, yes, then the team can do 1 feature a week.
Yeah, we are
So-
spending something under $100,000 per month For
100,000?
no 1,000.
Under 1,000, okay.
1,000. 1,000. 1,000.
Under 1,000 a month.
Under
okay.
under 1,000 a
Well,
month.
that seems like a good deal.
Yeah.
All right. Thank you.